Okay, this section is over numerical integration, and I'm calling it revisited because I actually discussed this in my Cal2 notes. So I'm just going to go ahead and get to it. There's two there's two techniques that you can use to evaluate an integral, and this is especially used when you have an integral, those non-elementary integrals that can't be integrated. So one technique is the trapezoidal rule, and the trapezoidal rule is actually developed by, rather than finding the area under a curve by using a rectangle, you actually find the area by summing up trapezoids. And so the number of trapezoids, the more trapezoids that you divide the interval into here, then the better the approximation will be. So let me just go ahead and give you the trapezoid rule. So the trapezoid rule for evaluating an integral is, if you want to evaluate the integral of f of x from a to b, then it's going to be b minus a over 2n, where n is basically the number of subintervals that you're going to use. So it's b minus a over 2n times f of x naught plus 2 times f of x1 plus 2 times f of x2 plus 2 times f of everything until you get back to f of xn. And x naught is actually, that's the same as a, and xn is actually the same as b. So I'll show you how to do this in the next example. So I'm going to do this. Now this integral that I'm going to do here, we actually can do this integral. In other words, we don't need numerical integration to evaluate this. You can evaluate this. So if you evaluate this integral from 1 to 2, which I did here, you can read that yourself. I got 6 2/3. Okay, but let's do the trapezoid rule with n equal 2, and then we'll also do it with n equal 4. Okay, now if n equals 2, then that just means we're going to have only 2 subintervals from a equal 1 to b equal 2. So we know n is 2, and so a is 1, b is 2. Those are the endpoints of the integral, the limits of the integral. And so delta x would be b minus a over n. So b minus a over n would be 1/2. Now I need that so that I know, because I'm going to start at the a value, which is 1, and then I need my delta x so that I can know where the next value would be in the subintervals. So the next value would be 1 plus 1/2, so that would be 1.5. And then the next point would be 1.5 plus 1/2, which is 2, and that's my right endpoint. So I basically only have 3 values, x0, x1, and x2. Okay, so now I can apply this formula, b minus a over 2n. So b minus a is just 1, and n is 2, so that b minus a over 2n would just be 1/4. So there's my 1/4. Okay, now I also have to figure out what is f of x0. So that means, now what is x0 in our example? It's 1. So I have to find out, okay, what is f of 1? So I plug 1 into this function. So 9 minus 1 squared is 8. Then I have to find, okay, what is f of 1.5? So plug 1.5 into the function. 9 minus 1.5 squared was 6.75. And then figure out what is f of 2. Well, f of 2 would be 9 minus 2 squared, which is 5. So now I know, using this formula, it's going to be f of x0 plus 2 times f of x1, and then plus f of x2, because x2 is my last point. Okay, and then I sum all of that, and then I multiply it by 1/4, and I get 6.625. Now remember, the actual value, the exact value, is 6 2/3. So that's not too bad. Now, what if I do it with n equal 4? Well, if I do it with n equal 4, then with n equal 4, the delta x would be 2 minus 1 over 4, or 1/4. And since 1/4 is 0.25, I'm just going to use 0.25. So x naught would be 1, and then the next point would be 1 plus 0.25, which is 1.25. Then the next point would be 1.25 plus 0.25, which is 1.5, and then add 0.25 to that, and you'll get 1.75, and then add 0.25 to that, and you'll get 2. So using the formula here, I'm going to have b minus a over 2n, which is going to be 1 over 2 times 4, which is 1/8. So there's the fraction that I have out front. Now I'm going to have to figure out what is f of 1, what is f of 1.25, what is f of 1.5, what is f of 1.75, and what is f of 2. So anyway, you know, to find these values, you just plug these numbers 1, 1.25, 1.5, 1.75, and 2 into this function up here to get their values. Now, so I got the values, and the first value I just put there. So there's f of, right there is f of x naught, or f of 1. So I have f of 1, then plus 2 times f of 1.25, plus 2 times f of 1.5, plus 2 times f of 1.75, and then plus f of 2. And then add all of that up, and then multiply it by 1/8, and you get 6.656, which rounds to 6.66, which is even closer to the value that I got. Now, of course, this is actually designed for functions that are very difficult or impossible to integrate. So let's say I took let's say I had a function like this, square root of 1 plus x squared, and I wanted to integrate it from 1 to 2 using n equal 4. Well, again, since I'm using the same limits, 1 to 2, then delta x would be 1/4 again. So I'd still have the same as I did in up here. I'd have 1, 1.25, 1.5, 1.75, and 2. That would be my x values. And then what I would do is I would evaluate this function, square root of 1 plus x squared, at each of these numbers. Now, you can check my work, but I got f of 1 equals square root of 2. F of 1.25 is the square root of 2.5625. F of 1.5 is the square root of 3.25. F of 1.75 would be the square root of 4.0625. F of 2 would be square root of 5, and so forth. And so I still have 1/8 again for the b minus a over 2n, and then I have square root of 2. That's f of 1, and then plus 2 times f of 1.25, plus 2 times f of 1.5, plus 2 times f of 1.75, and then plus f of 2. And so remember, the first point, the first term and the last term, you don't multiply by 2. Okay, so you add all those up, and then you multiply by 1/8. And so I got approximately 1.811 for that approximation. And so that's the trapezoid rule. Okay, now the Simpson's rule, it actually tries to, instead of doing rectangles or trapezoids, it tries to fit little curves here. So I won't worry about trying to explain how it's developed. But here is Simpson's rule. The Simpson's rule, you multiply by b minus a over 3n, and then you have f of x naught, and then 4f of x1, then plus 2f of x2, plus 4f of x3, and so forth. Now, n has to be an even number on Simpson's rule. Okay, so basically the first term here is not multiplied by anything, and the last term here is not multiplied by any constant. But when you start here, it goes 4, 2, 4, 2, and so forth. And so it alternates between 4 and 2. So you start with 4 and then alternate to 2 and then 4 and so forth. Okay, let's look at an example. Okay, so let's do this example we did earlier. So let's do this with n equals 2 and n equals 4. So actually, let's see, I'm not going to do n equal 2, I'm just going to do n equal 4. So here, if I apply Simpson's rule here with n equal 4, well, I'm still going to have the same subintervals. X0's 1, X1 is going to be 1.25, X2 is 1.5, X3 is 1.75, and X4 is going to be 2. And then when I do b minus a over 3n, I'm actually going to get 1/12. So b minus a over 3n is going to be 1/12. So evaluate this function at each of these values, okay, to get your functional values, and then you're going to do 1/12. That's the b minus a over 3n, and then here you're going to have f of 1, and then remember we start with 4 times f of 1.25. And then we switch to 2 times f of 1.5, and then 4 times f of 1.75, and then you end with just f of 2. Okay, and then you add all those up and multiply it by a 12th, and look, you get exactly 6 2/3. So Simpson's rule gets you there much quicker. So Simpson's rule, it'll get you there much quicker. Here's another example here. What if I want to integrate sine x from 0 to pi using Simpson's rule? Okay, if I do n equal 4, okay, well first of all realize that pi over 4 would be delta x. So if I go from 0 to pi, then I would go 0, and then I would move pi over 4 to the right to get pi over 4, then move another pi over 4 to the right to get pi over 2, and then move another pi over 4 to the right to get 3 pi over 4, and then finally move another pi over 4 and I'd get to pi. And so then I figure out, well, what's f of 0, and then I figure out what's f of pi over 4, and then what's f of pi over 2, what's f of 3 pi over 4, and what's f of pi. And of course I'm just plugging these values into the sine x function. Okay, so then you have to do b minus a over 3n, which is just going to be b minus a is pi, and then 3n would be 12, so you'd have pi over 12 out here. And then on the inside you would have f of 0, and then plus 4f of pi over 4, and then plus 2 times f of pi over 1, then plus 4 times f of 3 pi over 4, and then plus f of pi. And then you add these up, multiply by pi over 12, and you're going to get 2.005. Okay, and so you can try it again with n equals 6 if you like. Okay, now on the next video I'm going to actually do some of these with non-elementary integrals. The integrals I've worked with so far, actually most of them could be integrated with regular techniques, and you wouldn't have to use numerical methods. But in the next video, the ones I'm going to do, you basically have to use numerical methods to integrate.